All right. Well, we're back and just about ready to get started with the hands-on session that will run for the next 3 hours. And Hugh Pollitt-Smith from CMC, who's also the chair of our hardware task group, will be leading that session. We'll have speakers from Embakaz and Ashling talking about toolchain and IDE environment and the whole FPGA bring-up environment. If you have questions, you can put them into the question section on the side. You'll also see underneath the viewing panel that there are links to breakout rooms. Don't go there yet. As each speaker gives their talk, we'll break out into the breakout rooms to make it easier to have an interactive discussion and try to replicate, being in a hands-on environment as much as we can. And you can just go into those breakout rooms as directed by Hugh and the speakers that are coming up. Also, at the end of the session, end of the day, once OSDForum wraps up, you'll get an email with a link to a questionnaire and evaluation form that really helps us improve these kinds of events. So please be on the lookout for that and take the time to complete it and give us your feedback. So with that, I'll throw it over to Hugh and have fun playing with the hardware and environment this afternoon.
Okay, thanks, Rick. So as Rick mentioned, I guess this hands-on session is broken up into a few sections of presentations, and then the rest, most of the time is dedicated to sort of hands-on or discussions throughout the 3-hour period. So I'm going to start off with a presentation on the Core 5 MCU FPGA platform, which Florian mentioned a bit earlier today. And then so I'll probably take about 10 or 15 minutes for that. And then in 45 minutes, we'll have Embakaz providing a presentation on the Core 5 toolchain, and then 45 minutes after that, Ashling will give a presentation on the Core 5 IDE. So in terms of my presentation, I'm going to give a little bit of information about CMC Microsystems, describe the architecture of the Core 5 MCU FPGA platform, talk about the platform development environment, the platform setup, give a quick demo on how to build and run an application on the FPGA platform, and then just describe next steps in terms of how to get involved with this ecosystem. CMC Microsystems is a not-for-profit organization based in Canada that supports microsystems research involving design, manufacturing, and testing of microsystems devices and systems. We're the manager of Canada's National Design Network, which involves 67 universities and colleges, connecting 10,000 academic participants and 1,000 companies with whom they're collaborating to make and test these micro nanosystem prototypes. Many of our products and services are targeted to Canadian academics, but we are increasingly providing these capabilities to researchers outside of Canada, as well as startups and commercial organizations. In terms of the products and services that we provide, we've got them divided, I guess, under 3 banners: CAD, Fab, and Lab. In terms of CAD, we deliver access to hundreds of design tools and design modules for design and verification of these microsystems components and systems. They're available on researchers' desktops or through CMC's secure cloud compute infrastructure. We deliver user guides, training, and workshops on these tools and flows as well. For Fab, we deliver multi-project wafer services and affordable access to foundries worldwide in microelectronics, silicon photonics, and MEMS, perhaps relevant to some of today's discussions. We're the channel partner and MPW reseller for Global Foundries in the Americas, which includes the 22 nanometer FDX technology that will be used within the Open Hardware Group silicon efforts. We also provide fabrication and travel assistance to university-based fabrication labs and assembly and packaging services. And finally, in Lab, we provide test equipment through our equipment rental program FPGA development platforms on site or in the cloud. We have a cloud-based FPGA GPU cluster for accelerating algorithms such as machine learning and machine vision. And most recently, we now provide access to quantum programmers through the IBM Q-Hub and University of Sherbrooke so that researchers can access quantum computer. So now I'll talk about the architecture of the Core 5 MCU FPGA, and actually I probably don't need to because it was addressed quite a detailed manner this morning, so I really won't go into detail on that. So in terms of the Core 5 MCU repo, I just highlight some of the information that's in there. There's a doc directory where you'll find the data sheet for the Pulpissimo platform, which may be useful to refer to. There's an FPGA subdirectory, and a lot of the instructions for the using and programming the FPGA platform will be in the README file there. There are pre-built bit streams for the CV32E40P platform in the subdirectory there, as well as the Pulpissimo platform, which gives sort of the top-level RTL for the FPGA platform. And then there's several directories for the specific FPGA boards that are supported, including the Pulpissimo Nexus board. When the Core 5 MCU platform is installed, there'll be a IPs subdirectory, which includes a lot of the RTL for the infrastructure for the platform, the peripheral blocks, memory, and all that kind of stuff. There's also a simulation directory, which has model sim and Questa sim simulation capabilities as well. In terms of the IPs that are provided, there's debug interface, there's a APB interrupt controller, the CV32E40P core. If you follow the instructions, that will also be instantiated within this directory. And the Pulp SoC subdirectory includes the RTL that will instantiate the CV32E40P within the platform. In terms of documentation you may find useful for today or beyond today, the CV32E40P documentation is online in the repo there, and includes all the information for that core. And then, as I mentioned, the data sheet for the Core 5 MCU Pulpissimo platform is in the Core 5 MCU repo. In terms of the development environment, the supported environment for Core 5 MCU is Ubuntu 18.04. For the FPGA build, we use the Xilinx Vivado tools, specifically version 2019.2. For the Nexus A7 platform, the free Xilinx Webpack is sufficient to run the build for that. If you're using other boards such as Genesis 2, you'd need a full license for Vivado. As I mentioned, simulation libraries are available for Mentor Graphics Questa Sim or Model Sim. The Core 5 GCC toolchain, we're using a pre-built version from Emicosm. And as Florian mentioned earlier today as well, there's a Pulp runtime and a Pulp SDK that are available. The Pulp SDK provides the OpenOCD tool for connecting the debugger to the platform. In terms of the platform setup, we're using the Digilent Nexus A7 100T board. It's got some of the relevant features for today. The shared UART JTAG port and the Digilent JTAG HS2 cable should be connected to your host system. We've used the Xilinx Vivado tools for downloading. If you don't want to install the Xilinx Vivado tools or have had some issues installing it, you can also copy the pre-built bit streams onto a micro SD card or onto a USB thumb drive and insert it in either the micro SD port or the USB host. And you have to configure the programming mode jumper to set it to either JTAG or USB SD mode. And if you're using the USB mode, you'll also have to move this jumper from the SD to the USB pins. The board also includes PMOD connectors. We're using one of the PMOD connectors to connect the JTAG cable to that, but you can also use other PMOD connectors in the future to integrate other peripherals such as Bluetooth or various sensors that are available. Digilent provides a lot of low-cost PMOD modules for the board. The power is derived through the program UART cable. You can just switch it on once you've connected that cable. So now we'll run a short demo to illustrate how to program the FPGA and then compile and run an application. So this will just show how to launch the Vivado tools. There may be a trick when programming via Vivado. There's sort of two modules, two targets within the chain, and you want to, depending on how the USB ports are configured, it may fail through auto check. So you go in to open a target and auto connect. You'll see there's two targets. In this case, it fails, so you have to sort of close one target, open the second target. It should auto detect. And then you can program the device using the bitstream file that you've either created or using the pre-built ones. Once you've programmed the board, you should see the green LEDs light up on the board to confirm that it's been programmed. You can quit Vivado at that point. You can then go into the Pulpissimo Nexus subdirectory. You'll see there's an OpenOCD Nexus HS2 configuration file. You can use that to configure OpenOCD and launch that. If you go too fast, then you might get an error. So you just try it again. And you'll see that we're using HART number 992. In this configuration, that's preset by Pulpissimo platform or the Core 5 MCU platform. Once you've got OpenOCD connected, you can go to the, in this case, a simple sort application. Using the Pulp runtime, you can build the application, and then you can use GDB. And you can connect to the target. On port 3333, load the application. You can use the monitor command to view all the registers, or you can use it also to view the value of some of the registers, any of the registers. You can view the C source file. You can set breakpoints. You can run the program, step through the code or go next. In the terminal window, you can see the output of the printfs. You can also view the disassembly code. You can view the value of the local variables and sort and array. And that is about it for the demo. So in terms of the steps that were I guess provided in the FPGA subfolder of the Core 5 MCU, there's instructions to install the environment, all the tools, install and modify the Pulpissimo platform to instantiate the CV32E40P core and build the FPGA bitstream, instructions to download and pre-built FPGA bitstream or the bitstream that you've created, and build and run an application. I should also mention there's also instructions how to run a Quest-to-Sim simulation in those instructions. In terms of next steps for this environment, as with all the open hardware projects, I'd encourage you to get involved and contribute. Start using the platform, provide feedback, raise issues, create pull requests to the repo. These can help enhance the architecture, or you can integrate some of the board peripherals, develop device drivers for those peripherals to create a more rounded environment, demonstrate new tools, whether they're hardware, debug cables, or software, IDEs, operating systems, whatever within this environment, and help develop the runtime and the software development kit for this platform, and also develop applications and demos that we can use to illustrate this environment better. That's all I have. So I guess we'll now go into the breakouts, or go into the discussion. I guess we should look at the any questions in the chat yet. So I believe the next presentation will take place at 2 p.m. Eastern, which will be Embicosm. So from now until then, you can go into the breakouts or use the chat to ask questions about the environment and start using the board. So thank you.
Okay, I'm going to chime in here and answer one of the questions that came in on the chat window in the main session. The verification environment that we have for the RTL that we're working on is in a repo called Core5Verif. I talked about it a little bit this morning during my intro, and it's a full System Verilog UVM-based verification test bench that runs against commercial quality System Verilog tools and simulators. So it runs with all the big 3 CAD System Verilog environments, simulation environments from Cadence, Synopsys, and Mentor, as well as with metrics on the cloud using DSIM. So we have a test bench that runs, a CI-based test bench that runs with continuous integration and regressions overnight, every night, as new test cases get added to the test bench and committed into the verification master branch that then triggers the overnight regressions. And it's a full step and compare System Verilog UVM environment in that the DUT, the test programs that it's a full step and compare test bench that has the execution program, the test program that's being executed in the device under test is that same test program is being executed on the Paris golden reference model for the RISC-V ISA. And at the retire of each instruction, we step through and compare the CSR's program counter and the whole status of the machine on a instruction by instruction basis. So it's quite a good verification environment. We've actually found a number of bugs as soon as we turned on step and compare that were previously passing tests that were being run on directed tests. And that whole verification environment is available for anyone to use with any RISC-V implementation. We've developed it, and we believe over time it will become the most comprehensive and robust verification platform for RISC-V cores anywhere. So go to the Open Hardware Group repo on GitHub and navigate to the Core5 Verif repo, and you'll see all of the description of that environment and how to participate. And I'll see if I can put that in the chat box as well. And I'm not sure, sorry, Logi or Logi, hopefully that I've got your name right and that answered your question. If not, enter any additional tools on, enter any additional questions you might have on the chat room questions section.